Now, we remember from last week that a series is an expression that looks like an infinite sum. So we have some expression that looks like the sum, let's say, from n equals 1 to infinity of terms an. Right, this, I want you to think of it as being secretly, right here we have a1 plus a2 plus a3 plus a4, etc. Right, so that's what it means when we talk about an infinite series. And associated to this series, right, this is an expression that may or may not mean something, but associated to that we get a sequence of partial sums. So we say the partial sum sk is defined by saying that we truncate our sum after we take k terms. So for instance, in our previous example here, S3 would be A1 plus A2 plus A3. Now, again from last week, we saw that a series converges if the limit of the partial sums exists. Right? So if it exists, and then I'm going to name that limit, I'm going to call it capital L. And we say the series converges if this limit L exists, and so it needs to exist, and we need that L is a number. Right, so L can't be infinite, right, and also can't be minus infinity either, right? It has to be a number. And if we have a finite limit, and it's this number L, then what we do is we say that the series, the sum from n equals 1 to infinity of an, is equal to L. Right? So that's what we do. We say that if this limit exists, then that is the value of the series. And we're going to write as shorthand, right? So we're going to write as shorthand to say that this exists. Right? If L exists, we will sometimes write that the sum, right, so from n equals 1 to infinity of an, we will write that it's finite. Is less than plus infinity. What that means is that that limit L exists, right? That's a shorthand notation for that. Okay, so we have several goals. There is the strong goal, and the strong goal is to actually figure out what the limit is. Right, so there are going to be some examples. We'll see one in a moment, and then in a next video we'll see another kind of example where we can find it. So those are going to be the good cases, right? The good cases, we can find the limit directly. So that's the good case. And so I'm going to draw a little smiley face. Right, so we're happy. We're happy because we can find the limit directly. And then the thing is, in most cases, it'll be really hard to find the limit directly. And instead what we're going to do is we're going to break it into a two-part process. So step one is determining if the series converges or not, so if that limit L exists or not. And then the second half of it is going to be finding approximations. So this is, let me say this is just sort of the okay case. And I'll draw a flat mouth, right? That's the good case is going to make us very happy. This case, unfortunately, is the typical one. So that is what it is. There's no such thing as a free lunch. We're gonna have to work a little bit to deal with this. Okay, so an overview now then of section 10.3 is that we're going to be looking at two types of series we can compute explicitly. And to be honest, these are going to be essentially the only two kinds of examples we can compute explicitly in this class. If you study some more related topics down the road, you'll see there are other examples that are computable explicitly, but there are not that many that are computable explicitly. So this is, we'll see the two that we can deal with in this. Well, so this video will focus on geometric series, and then a later video will focus on telescoping series. Okay, so let's talk about geometric series. So this is section 10.3.1 in the textbook. And let's start with the definition. We call a geometric series any series that looks like a constant times r to the n, where r is also a constant. Right? So for example, we had a story of a frog who was jumping half the distance at each go, and he was jumping, I think he had 1 plus a half plus a quarter plus an eighth, and so forth. Right, so this language of common ratio is coming from the fact that the ratio between, let's say, that term and the next one, the ratio is 1/2. And that one is also a half, and that one is also a half. Right, so that's where this language of common ratio comes from. So that's an example of a geometric series. And here I have several examples. Right, so this first example here, 1 over 4 to the n, we can take c equals 1 and r equals a quarter. This next one, 7 over 3 to the n, we can take c equals 7, r equals 1/3. Okay, so these are both obviously, the first two are just obviously geometric series. The next one is a geometric series, but it's a little bit off, right? It doesn't start at n equals 0. So for this, we're going to rewrite it. And this we can write, right, so this looks like 5 over 4, right? That's n equals 2, we get 5 over 4. And then at n equals 3, we're going to get 5 over 8. And then at n equals 4, we're going to get 5 over 16. So on and so forth. And now what we can do is we can factor out this 5 over 4, and we can see this now as 1 plus 1/2 plus a quarter, etc. So we can see this as having common ratio, so that's common ratio r equals 1/2, and that constant c is going to be equal to 5/4. And so that's an example of a less than obvious example of a geometric series. And now this last one, right, this 0.78787878787878 with this repeating decimal, that one's maybe not obviously at all a geometric series, but it is. All of these repeating decimals can be understood as geometric series. So let's go ahead and analyze that in a little bit more detail. Okay, so we consider now this decimal, 0.78. And I'm going to start with this decimal. This is 78 over 100. Now, that's not really the one we want. We want 0.78 7, 8, 7, 8, etc. So what we're going to do is we're going to write it, right? That thing is equal to the sum of this guy plus that guy plus this guy, and so on and so forth. Right? And he's equal to, that's now 78 over, okay, we need 1 with 4 zeros, right? So 10,000, which I am going to write as 100 squared. And this is now 78 over 100 cubed, and so on and so forth. So what we're getting out of this is that our number here, this thing, is equal to 78 over 100 plus 78 over 100 squared plus 78 over 100 cubed, etc. So this means that we can see our decimal as a geometric series. And this is a geometric series. And it has the ratio equal 1 over 100. Right? That ratio is 1 over 100. And the constant is going to be 78 over 100. Right? This constant c is 78 over 100. And right, the way we see that, going back to our previous page, right, if we go here to a geometric series, this series, as written, starts with c plus cr plus cr squared, etc. Right, so the ratio, the common ratio, you can read off just by looking at what gets raised to the power n, and the constant then is whatever that first term is. So that's how we figure out what c and r are in these geometric series.